All right. Hello, everyone. This is a technical walkthrough call with one of the projects who is part of the Ethereum Attackathon, which is probably going to be live at this point of time when you're going to watch this recording. And we're having Dustin from Nimbus ETH2. Dustin is going to cover the main aspects of the protocol today, the most interesting parts for you guys, for the security researchers, on where to spend the most time searching for bugs. And we'll also, have some conversation about certain parts of the code. I will probably ask some questions. So enjoy this video. Dustin, welcome. Thank you for joining, and please go ahead with presenting an explanation.
Great. Yeah. So thanks for the invitation. And so yeah, I work on Nimbus ETH2, and so this is one of the I guess to broadly situated, it's one of the several consensus layer Ethereum clients. And so this is the beacon, also known as the beacon chain protocol. And so it is an implementation of this. And so if people, within the Ethereum ecosystem, this is the part of the Ethereum ecosystem that deals with attestations and sort of sync committees. It deals with sort of gossip in the sense of sort of sending around these blocks and everything else. So yeah, this is, and so Ethereum, and it is generally paired with an execution layer, and this is not what we're going to be talking about here today. Those also exist as Geth, Nethermind, Aragon, Reth, etc. Those are separate protocols, and that is important to understand. I think that what Nimbus ETH2 implements is very specifically the consensus layer protocol. And so it is a network application. It speaks. Let's see. Yeah. Okay. So yeah, and it's basically its interfaces the external world which is kind of, if from an attacking perspective, I think the first salient thing are a few. One, it's this gossip layer, and this part is going to be largely shared. I will say, just to start with, to orient among all the CLs, so they all speak the gossip protocol, etc. The gossip layer. So this is a mesh network overlay network on top of the internet, based on P2P. So if attacks can go through that, those are effective if you can make them work. It speaks also. There's a beacon API. This is a REST server, an HTTP essentially HTTP REST server, and so this is another potential avenue of attack. The challenge with this is that typically these are not broadly shared on the internet, and so in fact, if and technical question for a moment, is my screen visible like right now?
Yes.
Okay,
good.
great.
Please continue.
Yeah. Okay. So because I want to show something here is that, so if we look at this, so we just release, just today, and this thing here, this was in theory, a security bug. Now it's fixed. It's all public. You can see. Now, however, despite being trivially exploitable, if you can feed this JSON to the application, it's actually quite a challenge, because in ordinary circumstances, because it depends on accessing this REST server. So, and that's typically localhost only. So that is an example of, so it's a softer target if you can get at it, but typically people who host these beacon nodes publicly put a proxy in front of them and filter things. So not, yeah. So there's that. It's a client to other things. It's a client to the builder API. If you can host a fake builder relay, then that's a way you can feed it responses. That's JSON. So anyways, there are a few of these. So that's sort of the overall kind of how it sees the world. It's through these interfaces. So the broadly and so I guess okay. And so and as such, broadly speaking, one way to look at the code base is that it has a trusted and untrusted part. So we can look at, for example, everything in this gossip processing part. everything in here is essentially treats things as untrusted. So when batch validation, block processor, ETH2 processor, gossip validation, light client processor, etc., they see things coming in, they do not yet trust it. So on the one hand, easier to access these. On the other hand, they are in theory hardened. So, I mean, if we look at gossip validation, all gossip validation is a bunch of if this is invalid, then fail. That's the entire module here. Thousands of lines of this. So, on the other hand, there are other parts of the application which are, if you can get things, if you can find your way into, state transition epoch, this is quite a bit of a softer target. Right? So, because what happens is we have a bridge. We have at some point what we have is a function that or a barrier where we check and then we trust, and then we treat things in a trusted way. So that is broadly I would say, if at a very high level architectural overview, that's the most important thing to note, is that there's a trusted part and untrusted part, and no part you want to attack. So and each has trade-offs. So the other thing is, I'm not going to demonstrate this here, but libp2p attacks are certainly possible. It is a project we use, libp2p. It is more or less part of the code base, but it is not something I'm personally an expert on, and it is not literally Nimbus ETH2. So, but it is certainly something worth looking at. It implements this gossip protocol. So I think that's I kind of stop for a moment as I say, asks for sort of basically, I mean, I can continue going through this kind of outline here, or but say, is this, yeah.
I think we're moving in the right direction, Dustin. So yeah, I agree that, thanks for highlighting the parts that you think are, the most important for attack, or I guess the most attackable. But maybe, a bit of a high level on the code. So
Okay.
can you talk a bit more about Nimbus itself? So as you said, it's different from Aragon, it's different from Ref, and actually, just for your information, of others, we're going to have a separate technical walkthrough course for technical deep dives into those code bases. But about Nimbus itself, so can you tell us like how it differs from other projects that you mentioned? What's the the core functionality here? Yeah.
Sure. So the basic way of looking at Nimbus in this regard, certainly compared to Reth or Aragon, is so it implements these. Nimbus, the simplest high level way of looking at Nimbus is, and this also affects how to plan an attack on it, say, is it implements the consensus specs. It is an implementation of these specifications, and if one looks through the code base, in fact, there are many kind of back pointers, URL links to exactly this repo, which say this implements this part of this repo. So I mean, for basically anything here, and I'm just kind of randomly clicking at the moment. I'm not gonna, but this thing here, this function here, this is eligible for activation queue. Nimbus has it in very direct form, and that's basically true for everything in the specs folder here of the consensus specs. Now, this is Reth and Aragon and Geth. They're an implementation of what I would. It's a little more diffuse to find the specs for these, but essentially the execution layer. So Nimbus is a consensus layer client. They are execution layer clients, so they implement a different set of specs. So yes. So this is to start with. How and Nimbus is largely organized along the lines of these specs. So Nimbus, in fact, has like here where, for example, and again, I'm just gonna there's a whole set of these epoch processing and how much is introduced differs from fork to fork here. So Deneb didn't actually introduce that much epoch processing, but Nimbus has a module called state transition epoch, which implements precisely this epoch processing section. it has, similarly, if we scroll up slightly, is block processing. It has a module called state transition block that implements precisely block processing. So it is very much, so if you want to kind of understand the organization of the Nimbus repository and Nimbus as an application, I think it helps a lot to understand this consensus specs repo. And I think that's the first major resource I would point to. And this is true, by the way, also of the other consensus layer clients. That they all implement, they are all implementations of this set of specifications. So I don't know if that's addresses that question at a high level, perhaps.
Yeah, sure.
So in fact, well, if we look at Nimbus to want to map that to Nimbus, so first, the rest of these folders are a little bit of separate things. The interesting stuff's almost all in beacon chain, just to start with. And so things which are in spec. So here's one thing. Things which are in spec are largely mapped almost one-to-one with things here. Almost often we try to make it function name to function name, variable name to variable name when we can, when it's efficient enough to do so. So, I mean, these are signatures with any of these. These are exactly from spec. I mean, this straight up implement just the spec. Now, this is what I think the main, probably the main thing that's sort of to start by highlighting is if one looks at block processor, I think in terms of understanding the security aspects of Nimbus, this is sort of the key thing. So I was talking before about, so the idea you have a trusted world and an untrusted world. This delineates the two. So if you want to attack the trusted world, you have to first get your block past this. And in particular, the important part of this is essentially it does store block. We have somewhat long function names here. So it's somewhat long functions. But this store block function, for example, and this essentially implements this. This can be regarded as this kind of barrier, as the gatekeeper. So it takes an untrusted block and ultimately creates a trusted block out of it. We actually have literally types called trusted and well, not untrusted, but we have not quote unquote trusted and we have trusted blocks. And this is the dividing line between the two. This sends them along. So that's so this on the one side of the, sorry, I apologize. On one side of that, what you have is the best of gossip processing. And the rest of the gossip processing is all the untrusted stuff. Then it goes to the block processor and it becomes trusted. And then on the other side of that, you have the consensus object pools, you have the spec, you have fork choice. So this is, yeah. Let's see. And so now the reward. So the way, yeah. The key way that the beacon chain operates is every 12 seconds it sends along a block. Other clients vote for this block at 4 seconds theoretically, and then voted for blocks get through. And so this is important to hit 4 seconds because there's several conditions. Different parts of the spec very much mitigate towards 4 seconds being the boundary on this. And then every 12 seconds the chain progresses. So this is the basic structure of how things move forward. And so that the basic structure of an attack is somehow, if it's an attack on the network as a whole, you have to stop that chain from moving forward. That's how that works. If the chain doesn't stop moving forward, it's not that much of an effective attack at some level. So, and this is this function which ultimately determines this. Everything else is this kind of store block function. So, and yeah, and so, I mean, yeah, I guess I can go into more of that, but I guess I'll just say, like, for the introduction to this, there's rewards and boost duration, and some of those are maybe a little bit, I don't know, I can get into them, but currently they feel like a little in the weeds. But
I feel like, yeah, Dustin, we can move on from the like high level scope of the protocol. Yeah, and thank you so much for presenting this. Let me ask you a question that may help us with further direction here.
yeah,
So, can you please tell me, were there any audits done on the code already? And if yes, what were the outcomes and bugs found, if any, again?
sure, absolutely. So the answer is yes, but an ancient amount of time ago in blockchain terms, 2020, I want to say. This is all all in the repo here. So if we look at the NBC audit, so this happened. There was an audit, and indeed, so in terms of what issues that were found, the easiest way to start finding some of these things is, and these are all actually, the way we did the audit was we had them file issues in our GitHub, so they are still in our GitHub. Most of them are closed, but they are still there. But you can look in book by tags and see what's there, and we can get an example. So, and keeping in mind that these are, again, 2020, so the exact issues are very different, but they were a number of these things. For example, one whole category, a theme genre here was we had a number of unbounded quarantines, unbounded buffers, let's say, quarantine being a Nimbus sort of term of art, but an unbounded buffers of sort of unprocessed blocks, and these days they would be blobs or attestations, and those were attackable and fairly trivially, just memory exhaustion attacks. So we did fix those, but those are examples of what was found. There were, we can see elsewhere here, our JSON RPC at the time was not very hardened. We had a number of sort of, it didn't check for directory sort of permissions being correct. It's not on this screenshot, but elsewhere. In general, it was sort of, and in fact, if we looked at the closed bugs, we can see many more. There were a number of sort of invalid sort of acceptances of things that should have been valid, are sort of invalid, and vice versa. And so this is actually kind of key here, because another way of attack. So blockchain in general is a consensus protocol, and anything that violates consensus is an attack point. It means that even if you don't crash the client, then if Nimbus gets sort of veers off onto its own path, well, that's an attack. It's not following the chain anymore, and it's not getting the rewards, and it's not participating. And so a number of these were that. So we either, in both directions, we have here the incorrect surrounding checks leading to discard valid attestations. That's one way of not following the chain. And similarly, incorrect check on linked list insertion can lead to accepting invalid attestations. That's another way of not following the chain. So type 1 and type 2 errors, so to speak. They're both harmful. There's a number of cryptography things, and this is something I don't know. I mean, so this is something all the CLs use the same cryptography library, by the way, on this, BLAST, BLST. So high risk, high reward. It is hardened. It is a lot of attention on it. So if you can find something, congratulations. But it's going to be hard at this point. They've probably been auditing that one fairly in an ongoing way, and more or less. So not that there aren't bugs, but this is not a Nimbus issue anymore at that one point. So there are cryptography issues in theory, and we had some bugs in our usage of cryptography. So that's an example of what was found, and in general we've addressed them, I would say. But
Gotcha. Any other notable examples, notable findings that you want to highlight, or?
So I would say from the audit, I would say I think we've kind of resolved by and large what those were. I think there have been notable things, and when we look at, I would say what has proven to be an actual attack of significance, sort of in the history of Nimbus is, so there are, so gossip, which does not depend on cryptography, and I think DOS attacks have proven to be pretty effective. So I would say, so first to go through things which are in theory are, if you can find them, again, that's great, but pretty specialized. Fork choice is potentially existential, but also it is extremely scrutinized. And so again, this is something that is, if one, and Nimbus just follows fork choice specifications, and I can here, well, oh, I see. Yeah, the fork choice specifications, but so if one can find holes in that, ways to create Yorks, those are high value for sure, but I would say a little bit out of scope of what first I can directly address here. Secondly, less likely to be found. But so if one does want to look for them, I will just say that they are in fork choice. They are here. But as you can see, there's not a lot of code here. This is very much a conceptual attack, or this is a more mathy attack. It's figuring out the holes in the proofs, let's say. And there are proofs, by the way, for a lot of the fork choice. There are proofs and theorems and the like. They're out there somewhere. So what I think has proven effective is things looking at gossip validation. So in particular, there's a weakness in, for example, validating a number of messages, attestations, blocks, which depend on reconstructing a block state. And so this involves a potentially expensive operation, differently expensive for different CLs, but for Nimbus, it can take seconds to do this. We do what we call state replace. We form the base state. So if you have a block that's going to apply to a state, or an attestation that's attesting to a state, based on a state, we have to reconstruct that state first, in some cases, to validate it. And this is an attack mechanism. People have used it casually. I'm a little surprised it hasn't been used more, but so it's not unknown. People have hardened it, and different clients have hardened it in different ways. But it's one of the places where I would say there's a potentially productive set of avenue of attacks on that one. That is very much kind of looking at the code here in this gossip validation, teasing it apart and figuring out how to trigger essentially DOS attacks with it. These are unauthenticated. These are kind of frontline kind of checks. So they deal with directly basically data off the wire, more or less. So I would say that's something notable. And when we've had attacks we've had to kind of take seriously, these are some of them. So that's maybe one thing I'd want to probably highlight.
Wonderful. I'd say let's move to the next part here, Dustin. Also, usually it's like very, very important for our white hats, is that are there any known issues, aka any open reports that for one reason or another you didn't fix, and those might be somewhere stored in your GitHub? If there are any, can you show them?
Yeah, so to some extent, and here it depends what one's threat model is, I suppose. And so is it local? Are you running on the same machine as a Nimbus client, like in some kind of virtualized way? Or is this a case of remote attack? But in particular, oh yeah, sorry, there's a couple of new ones here. But not to get sidetracked, but somewhere, yeah, okay. So here's a good example of And I'm just gonna like highlight like, and there are others. I don't. Okay, there are others, but this was a simple. These all came out of. There's a whole genre of bugs. These all came out of the audit to begin with. The idea of file system permission bugs, and for certain threat models, these are open because we're not really sure what to do with them, to be honest. And I mean, various people, I and other people, have kind of categorized these things, and I'm just going to sort of scroll through slowly to show these are all Nimbus issues here and all Nimbus PRs. And you can regard it as a bit of a, it's essentially bike shedding at this point. When somebody brings up that is it too strict or too loose? Should it automatically correct? Should it not automatically correct permissions? There's no obvious correct answer here. But you can see arguments and discussions going back years. So if somebody can, this is different tab. If somebody can figure out this, those are certainly open issues. We have others, I guess, but I think that's the that's probably the best example, I would say, of an issue that's sort of theoretically open. We have there are also and I guess it depends on the threat model, but the beacon node REST API has some extremely expensive, and we know this. And so we discuss internally. We treat this as a kind of a trusted attack surface for this reason, or trusted surface, I guess, for this reason. But I'd say looking at here. All right, this here beacon state 2, and another good resource, by the way, is if you go here. This is a reference for all of these things, right? So what this is, so I'll leave this up, and this is an extremely expensive call if done by JSON. It's hundreds of megabytes. It has to be gathered, encoded, sent, and even locally, it's kind of slow. So it's trivial to DOS a beacon node by just sending it a bunch of beacon state requests. So this is an example. Now, we don't have a GitHub issue filed over on it because it's not really a specific Nimbus vulnerability. It's just kind of how the spec works. But this is something to be aware of, that if one can access the REST API, there are a number of unauthenticated methods that are just slow. That's just how they are. And there are others as well. You can get validator status information. I think that might be in, yeah, here we are. Yep. So if you can, this is another one. So if you look at this endpoint, just request all the validators. There are 1 million active validators on the order of, and there's pushing 1.6, 1.7 something million non-active or active plus non-active validators, inactive validators. And so just ask for the status of all of them and do it over JSON. And then that will take at least several hundred milliseconds and up to seconds. And because Nimbus is a single-threaded application, you're blocking the event loop. But this is why we regard the BN as something that you usually would not run directly exposed to the internet in this side of, or the REST beacon API server, rather, as something that you wouldn't run usually publicly exposed. But if you can get at this thing, and I know there was a recent attack that people found going through some web browsers to kind of reverse proxy into local networks, then great, you know. What was it? No place like localhost or something like this. Then you can get at this thing and attack it on somebody else's network too. So that's something that can be. And one way to view these are not vulnerabilities which can never really be fixed in any obvious way. They're design flaws or not design trade-offs in the protocol. The beacon API fundamentally is designed as a trusted protocol. And there are many, many examples of it, to the point where it's not really a vulnerability if somebody finds like, hey, this beacon API call is slow. Yes, we know it's slow. but they are there. So yeah.
Got it. Thank you, Dustin. What else? What else? Is there any documentation that community can look at to better understand your code and code base?
Yeah, so I would start
Also,
with
one more important question is it up to date? Because usually hear that, some parts are not up to date, some of them are.
Yeah.
Yep.
Right. Yeah, so to some extent, yeah. So I'm going to start with this. So this is this nimbus.guide. I don't see it mirroring on my thing. Is it visible on? Okay. Hopefully people see nimbus.guide, the nimbus.guide website. I don't locally, so yeah.
Currently I see your GitHub, Dustin. Yeah.
Okay, got stuck. Maybe. Shares. There we go. Sorry, okay.
Yep, all good.
Got it. All right. I have to press the tab. Okay. Yeah. So now, this is just to start with. And that this is a user-oriented guide for sure. And so this is not, we have a security thing, but this is, and we mentioned the security audit here. That said, and so this gives some example, by the way, of examples to look at. This is sort of generic, and some of these are going to be a lot harder to find than others. So like, many people try to break BOS signatures, and people so far, there's not well, there have been attacks, but let's say there haven't been sufficiently effective attacks. So and all the others. So that's one thing. Now in the code base, and switching over to so okay. Okay, so now I'm going to switch. Okay, so I go to switch here. We do have sort of, if we look here, a bit. We have docs directory, and we have some examples. So we have so I don't know how visible this is, but for example, now let's see, I can. I don't know how readable, but anyway, people can see where in the repo it is. They can see the text that they want later. This is just a graph. This is a graph viz layout of some, and so we do document these things, and I would say they're reasonably up to date. They're still true. They're still yeah, image is outdated. Yeah, right. So as you say. We have not updated all of them, but I would say the charts and graphics are maybe less up to date, but the prose and the text here is pretty current, and so you can kind of see, and this describes exactly, just to give an example. So it describes this transformation. It goes from an attestation comes in, we verify it, and it becomes a trusted attestation, and then we treat it differently. And that's for attestation flow, and we look at block flow as well. And again, it's similar. We can go through. It's like it describes where blocks come from, gossip, B2, B2 database, etc. And this is a pretty good summary. For reference, when people see ETH2, think CL. This is just the ETH2 is the older branding. A couple of years ago, the EF changed this, but they're synonymous. There are. And again, so we do have these architectural diagrams, which are broadly correct. So yeah, and the names have changed in some cases, but the gossip flow is basically accurate. I mean, this is, and we go through and it describes what I've been getting at, and we have. So yeah, we do have some architectural documentation in this regard, and we have syncing as well. So how does syncing work? So again, this is the attacks on the sync manager are a little trickier to pull off because the sync manager reaches out to the world, and so you have to kind of be the lucky peer it requests some blocks from. But if you're ready and to return something a malicious response to it, then maybe it can work. So yeah, we have documentation kind of around the code base, and you basically look for markdown files, I guess. And yeah, so it definitely is there.
Wonderful, wonderful. Thank you for showing this. Let's see. Honestly, Dustin, I think we're in a pretty good shape at this point of time. Let's say that I'm totally done with my questions. Anything else that some final notes about the code base, something something that we may have missed?
Yeah. So first, I think here I actually want to say to get at something which may not be at all obvious, but I would suggest that, so people may have noticed that this is written in Nim, programming language Nim, that's fine. And it's a reasonably conventional language. There's the Nim documentation is actually pretty good. That's fine. There's ways of learning enough of it to get to understand the code base. So one thing I'll point out a couple of things that first, some parts of the code base I'm going to suggest are simply going to be difficult to, like the same way, I don't know, cryptography is a kind of specialized field, let's say, and it is unlikely that people are going to randomly come across things and find cryptographic flaws if they are not at some level a cryptographer. Anytime you see this kind of dim node kind of thing in the code base, that's sort of going to be like, you actually have to know Nim. You cannot just look at that and treat it as a weird, spelling of C. This is related to macros in Nim, AST macros like, Rust or Lisp or various languages have. And we use certain aspects of our code base use these sort of very, very intensively. So our networking sort of layer uses this a lot. We synthesize protocols out of these Nim macros, and to understand how to, what their weaknesses might be, actually does mean understanding. Like you see these add quote, this is macro code. So this is something to be aware of. It's a little more difficult to understand, the nuances of. So that's one. Another, though, is that Nim compiles through C, and this is an advantage. So for certain types of attacks, what one can do is, and I'm going to see if I can. I can't do that easily here. Sorry, I did the screen resizing thing there, but I realize I can't even show this easily. But essentially it compiles through C. Look for kind of a Nim cache directory, and you can kind of see what the C does. And in many cases, if there's a memory safety issue, if there's many categories of sort of programming issues will show up in this C code, and you can debug it like C. You can profile it. You can sort of instrument it, Valgrind, all of the rest. You can use the entire set of C-based tools. UBSAN, ASAN, all of these tools to just find potentially suspicious looking things. We try to do that too, but actually we don't run the ASAN too often, but we run UBSAN sort of semi-regularly in the CI and do try to fix those issues. But so that's something to be aware of, that it is very reasonable to use all that C-based tooling is available, and even people who develop Nim often primarily use for these kind of tasks C-based tooling. So don't rather than trying to find something NIM specific. So that's one issue, I would say. That's one, probably the main, maybe not super obvious thing. And so otherwise, so looking at the other, right. So I think it would be remiss to say, so looking at, this is the NIM document. Oh, I have to switch tabs. Okay, make sure when I'm screencasting here is aligned here. All right, this is pretty good, actually. I would say these resources is to go down to about language manual. I think past language manual, kind of going from top to bottom, left to right, it becomes more specialized. But through language manual, you can kind of get, all of these are fairly good resources in terms of learning NIM. The other really good NIM resource is this. This is NIM by example. This is just to get a sense of how things work. There's also, if people are familiar with Rosetta Stone, if there's moment. It has extensive NIM examples, and I will switch over okay, here, right? So there's lots and lots of NIM examples, and you can, kind of whatever it is you're looking at, you can get a sense of that. All right, so that's NIM, and we have so yeah, I guess looking at other things that come up. Access control in the protocol is largely based on this sort of gossip, the validating of valid messages plus sort of digital signatures. So this is one of the cases where I'll be honest and say, unless you're a cryptographer, I am not going to suggest going after VLS. It's too hard to target for the most part. It's cryptographers can and do, but it is not a general purpose sort of kind of, actually going to fuzz it and fall out with useful results, probably. So otherwise, I think, what other, in terms of complexity, in terms of the rest, I think this is kind of reasonably well.
Honestly, I think we covered a lot.
Yeah. I think, I mean, like, there are other parts, but honestly, a lot of them are, we use SQLite. SQLite is very well known. My guess is there's not a huge amount just to kind of see there from a security perspective, and a number of other aspects of this. There are other, like I'm going to suggest like this. Okay, right. So this whole EL thing, for example, this is just simply trusted. This is going to be. It's not that we are never attackable this way. There can and have been security vulnerabilities that are sort of exposed through this is a JSON RPC interface, basically, this EL interface, and where this Nimbus is the client, the EL is the server, and this EL server can send stuff back that in the past has been able to adversely affect Nimbus. The issue is this is a trusted relationship. This is explicitly defined in the Ethereum space as a trusted relationship. And so it's like, the idea is that whether it's one person or one organization, it's the same entity running both. And so, congratulations. If you want to crash your own Ethereum node by attaching a hostile EL to it, that's up to you. But like, we don't really consider that an attack, a viable attack on a CL usually. And if the EF bug bounty program, people are presumably familiar with this or should become familiar with it, we have a very similar set of criteria of what we consider an attack. So, and so things like the EL or the BN sort of REST API, we typically don't share those terribly viable attacks precisely because they have to be done as localhost via another entity one control. So if we look at the validator client, that's the other end of the REST API. That's the client to the REST for the REST API server in a way. But again, people typically run the same entity, the same person, the same organization is running both. So if you want to create a malicious hostile validator client that crashes your beacon node somehow, more power to you, I guess. But it's not really a security vulnerability exactly. Or at least if it is, it's a kind of low value security vulnerability typically. We try to prevent it, but again, the VC can just request, can spam a bunch of get state requests and kill the VN, and it is what it is. So we don't really try to protect very much against that. So I would say, yeah, gossip, and it's probably the most fruitful, among the most fruitful places to start. My suspicion.
Good. Yep. Dustin, thank you so much for this walkthrough.
Yep.
I think this will be very, very useful for our community and security researchers. Once
Okay.
again, this video and recording will go live in the next few weeks, give or take.
Great.
As for now, I think we can wrap this up. Let me stop the recording. Once again, thank you so much.
Yep.